Hi, I'm Dan from JBA, and what we've got here today are the JBA Trust physical models. So we're going to be looking at some of these physical models that are used for training and education in coastal and flood risk management. The one that we've got here today is the wave tank. Now the wave tank is usually used because in these situations in the coastal environment it gets really complicated and we can't always solve this through analytical equations. Now whilst it's very easy to predict how big waves are going to be in the offshore, when they start to move towards the coastline, all sorts of things happen to them. They start to interact with the bathymetry, coastal reefs and headlands. We get processes like shoaling and refraction and diffraction. We get depth-induced breaking. And that means by the time our waves actually get to the coastline, they're quite different to what they were offshore. And it's these nearshore waves that we're really interested in, because it's these nearshore waves that are going to interact with our coastal structures. They're going to lead to erosion, they're going to lead to wave overtopping, and eventually inundation or flooding of the communities that are sitting behind them. So what we've got here today with the wave tank, we're going to demonstrate the different defences that we can use. We're going to propagate 5 waves towards each of the defences, and we're going to calculate how much waves are going to overtop the defences. We're going to capture this, we're going to measure it, and we're going to see the different performance levels of all of the different structures. Right, now our first situation we're going to represent is our beach environment. Now normally when waves arrive at a beach, they're going to break and they're going to roll up and down the beach face, and there's not going to be any problem. Now today though, we've filled up the tank a little bit more and we're representing a storm surge. Now this means that there's deeper water, bigger waves are going to be arriving at our coast, and they've got the ability to roll up and down the beach, but they can also go over the dunes and inundate all the communities behind. So the first thing we're going to do, we're going to send our 5 waves down, we're going to have a look what happens. And what we saw is that even though the waves were breaking, there was still enough energy for them to roll up over the dunes, in this case fill up our reservoir. But in real life that would have meant that any houses or properties or communities behind the defence would have been completely flooded. And really that isn't an acceptable situation for us, so this is around the time where we bring in our coastal engineers. Alright, now we've just reset our tank, and now we can start testing some of our different defences. Now if there's only a little bit of wave overtopping, we can usually get away with just a vertical wall. If it's small in nature, it can easily just be set behind the dunes like we've just done there, or even incorporate into some dunes, and then that will essentially just provide another impermeable barrier to wave overtopping. Now we'll have a look how it goes. Now we did get still some overtopping, but it was a lot less than before. And we'll have a look how much we've actually got. Now what we've got here, we'll call that about 50 mil. And while it's only a little amount in our physical tank, this could easily be say 50 litres per second in real life. This is the sort of volume that will start leading to some problems. But still, it's better than if there was nothing behind there at all. And what we want to do now is see if we can try and improve the situation even more. So now we're ready to start designing some of our defences. Now the first thing we have to think about is what is the beach going to be like in the future. Now unfortunately when we're designing our structures they have to last 50, 100 years from now. So we have to assume a lot of the time that the beach is going to be very eroded or receded in those times, and we don't actually have any sand left. So we design to assume the worst case conditions. So our small wall has now turned into a really large wall. The crest height is the same, but all of the sand, all the sediment, all the beach in front of it has now gone. And this is what we're going to test first. How is that small wall going to perform under the same waves that we've just run? So we'll send our 5 waves down. Now this time we saw larger waves coming in. That's because they weren't breaking on the beach. They've actually hit the wall under really impulsive conditions. Now what we can do now is actually see how much wave overtopping happened and how much extra water that we've got. Now by removing the beach, we've now got about say 70 mils of overtopping. Now this is the exact same structural conditions, but we've just now got no wave breaking in front of the structure. So this is really important for our designs. But now we can use this as a base case to imagine this is what the conditions are going to be like 100 years from now. And now we can start changing the structural conditions to see if we can improve the situation. Now the next defence we're going to check and test is our sloped revetment. Now this is about a 1 in 2, also known as a dike. And what we're going to do is we're going to put it in front of our defence. Now the argument is that we're going to now induce more braking against it. The waves are then going to be smaller when they hit our defence, and it's going to have a better performance. Right, now we'll run our 5 waves through the tank. And what we've actually seen there is by putting the slope in front of the structure, we've actually made the overtopping worse. Where we thought the waves would break and dissipate their energy, they're actually hitting the structure, breaking right on it, and using it as a ramp to get over the defence itself. Now we'll just see how much water that we've got. Now what we've got is a completely full beaker, so we've made it consistently worse. Now we'll get that one back. Now this is one of the common myths that we see, that people think putting small slopes in front of a vertical wall is going to improve the situation. And what we find is about a 1 in 2, 1 in 1.5 is one of the worst conditions that we can get in relation to overtopping. Now there are a few ways that we can improve this coastal defence without changing any of the sediment properties or the slope in front of it. And the best way is to use a recurve wall. Now the beauty of this is it's not any higher or larger in the structure, but it's got this unique shape. Now this unique shape allows the water to come up, actually get captured in here and then shot back out to sea. And because of the nature of this, there's going to be less waves coming over the defence. Now we can show this by simply removing our vertical wall and clipping in our recurve. Now what we're going to do now is run our 5 waves again and see if there's any difference. And this time, what we've seen is the waves are actually getting shot back out to sea. There's probably the same amount of wave energy going up, but it's all returning out. So in terms of our safety and the inundation behind the defences, it's a lot better. And in fact, there was no water that actually came over at all. So something as simple as a recurve wall is a great way, a very cost-efficient way to improve a coastal flooding situation. Now the next defence we're going to be testing is our stepped revetment. Now this is at the same slope as our other revetment, except the only difference is this is essentially, it's got steps. We're going to see if these steps are going to change the performance of the defence. I've got that locked in, and we'll run our 5 waves. Now, there was still a lot of overtopping, and that's because we've still got that same gradient, that same slope that's letting the waves run up and hit the structure with a little bit more power. So this time, we see that we've got about 100 mils that's come over. So it's actually less than the sloped revetment, but still, it's not as good as the recurved wall. But now we're going to have a look if there's any other options that we can do. Now our last defence we're going to test today is our rock armour. This is all scaled down to fit into our model, but essentially it's representing a rubble mound structure that can go in place of the vertical structures altogether. Now we'll put it in our tank. Now we're going to run our 5 waves. And what we've found is actually the rock armour is a really good defence. It allows the wave energy to be absorbed. When the waves come up, they'll hit a rock, they'll go left, right, up, down, they'll hit another rock, they'll have to squeeze through gaps and change direction. And all the time they're really dissipating their energy. And when we have a look at the performance, we can see we've got very little, maybe about 5 mil. Rock armour is really effective. Now it's also cheap, but it has its drawbacks. You know, it covers up the beach, we get oyster growth, so it's always not the best option. So out of all of these, we've tested the rock armour, the stepped revetment, the sloped revetment and the recurved wall. We've found that all of these will have different performances. They can be handy in different situations, and it's always up to these physical tanks to test these environments and understand how each of them are going to react. And it's only when we actually get them tested in these situations that we are going to be able to do a cost-benefit analysis or an economic appraisal to find the best way that we're going to protect our coastline. Now, another thing we can look at is going further offshore. And in this situation, we've gone for a nearshore breakwater. Now, in reality, we can build a breakwater as high as we want, but it's going to be very expensive. We can completely block the waves if we want to, but it's going to also be unsightly. So in this case, we've got a submerged breakwater, and this one will actually sit under the water. So just put her in. And now this way, we can actually start to try and stop the wave energy before it hits our defence. So now again, we'll run our 5 waves. And even though the vertical wall before was one of the worst performing, by doing something offshore, we've now prevented all the wave overtopping. And the benefits of this has mean we've still got our beach, we've still got an area where we can go and enjoy, walk our dogs, but we're not having any of the drawbacks of having the rock armour in there. Now, building this offshore looks like a really good idea, but of course it has a large cost associated with it as well. So this is when we have to start thinking about the economics. Is it worth spending more money in an offshore environment or a little bit less money on the beach environment? So it's been a pleasure today showing you the JBA Trust wave tank and how it can be used to demonstrate wave processes and wave overtopping. And if you want to see the tank in person or for any more information, just get in touch with us via our website.